Okay, so this is our last lecture on the introduction to differential geometry course. So as discussed in the earlier session, today we plan to talk about the some of the applications of differential geometry in mechanics, mechanics, right? So the idea is we'll discuss about application of differential geometry in nonlinear mechanics. So we'll discuss about the uh, Rudd theories and so we'll begin with the discussion of Rudd theories. So at first, let me tell about in nonlinear mechanics, we usually use differential geometry to study problems in what we call as the slender structures. So application lies in slender structures, or more accurately, we can call it um, elastic slender structures. So the slender structures in general tend to be those structures in which there are variations in the dimensional scales, right? So say we have generally we define it in the three classes. So first we call as rods, ribbons, and plates, right? So we start with rods. So rods are those structures. So here we can call it plates or cells, right? To be more plates and cells rather, or and shells. So in rods, there are structures in which you have there is a dominant length scale, right? There is a dominant length scale, and the other length scales are just much lesser than that. So in a sense, say we have some sort of a cable, right? Just consider some cable, or even say the trunk of I mean, say a very long tree, right? As an example. And then you have these electric transmission cables or transmission wires and all. So they all can be classified as rods. So rods are those structures in which, so it will appear to be some sort of some sort of such structure, right? Where the cross-sectional dimensions is say some d, or maybe even we can call it d, which stands for diameter. And the length is sometimes characterized by say L, right? Or maybe capital L, whatever. So in rods, L is much larger than D. So it means that the length scale of the length L, or the dimension L, is much larger than D. So such structures are called rods. And examples can range, I mean, widely. In say in biological systems, they can be DNA molecules and muscle fibers, as an example. Even hairs, right? In engineering sciences, we use it for say cable, and they can range from say some sort of a cable-like behavior, right? So cables, then transmission wires and all that, right? They all fall under RUDs. Okay. So then there is another class of problems. Before I talk about ribbons, let's talk about plates and cells. So plates and cells, they are like some structures, say some sort of say let's have some flat plate, right? Right. So the length is say this is our length L, and this is say width W, right? And let this be small h. Now in such structures, it so happens that the length and width are of the same order. So the characteristic length or width are of the same order, and they are much larger than h, both of which are much larger than h. So h is our thickness. Likewise here, d is the diameter, L is the length. And L and W are correspondingly length and breadth, length or width. Right? So these such structures are called plates and cells. Then the last, in the list of three here. So the applications, for example, can, and of course, these are plates, and so the curved plates are also called as shells, right? So shell-like structures. Say, for example, a pressurized, say, pressurized sphere. And so they are shell-like structures, and even say, so these are like curved plates called cells. So they range from like you can have, for example, they appear in various forms. For example, in even aircraft fuselages, and so all these sandwich panels, right? And say pressurized containers, pressurized shells we can have. So there are many such examples. Right? So these are some examples of plates and cells. And essentially, if you go by the reasoning here, they appear like 2D. They are 2D in parametric space. So which means that we only take coordinates which just spans the length and along length and width. And height is just considered to be so small as if the entire mechanics of plates can be described by some sort of a mid plane, or which a plane which just lies between the upper and lower faces, right? So we have some sort of a mid plane or mid surface, we can call it. So the entire mechanics is as if lumped to that mid surface. And in RUDs, similarly, what we had is the entire mechanics of a RUD can be explained or can be lumped on to a uh, center line which just passes through the cross sections of every such every cross section of the RUD. Then we have ribbons. So ribbons are, and of course here, because of this parametric space, it is one dimensional in parametric space. Now talking about ribbons, so ribbons are narrow strips like, or they can also be called, said to be narrow plates, right? So they happen to be some plate-like structures, but width is such that right? And then say the width is T and the length is say L, and this width is say A. So in this case, the length scales are such that you will have L is much larger than A and much larger than T, right? So it is as if this is, of course, length, L is length, W is width, and T is thickness. So as ribbons lie between plates and uh, rods, so it is as if we are in a dimension which is between, I mean, in a sense, it's as if they lie between 1D and 2D. So sometimes we just call it ribbons to be 1.5D. In parametric space. And what you'll say is that ribbons can be approached through both ways. Either you can approach it from a um, from rod theory, or you can just model it as if it's a rod and with a center and which is passes through the mid surface and also between the midway in the along the width direction. And it so in that sense, it can be modeled as a rod with some lateral dimension, or otherwise we can approach it from plate, nonlinear plates theory, and then uh, just reduce the width, so to speak, just make it lower and lower, right? So that's one approach of dealing with. So there are two different ways of approaching the mechanics of ribbons. However, in general, what we tend to see in the literature is that it's usually preferred to model it from a rod perspective, that you consider everything to be lumped along the center line, and then as if you are adding some sort of a lateral dimensions. And in a sense, we are dealing with something what we had learned sometime back in this course with regard to the ruled surface. So it is as if we have a center line, which happens to be the curve, and the rulings or the generators tend to be along the width direction, right? And it just traverses through the along the curve. So that's what one way of doing it. So the applications are in things like what we call as say magnetic tapes. Right? So this were typically used in say audio recording and all, right, for audio recording purposes. And then they're also used in as actuators, such ribbon-like structures in actuators, right? So they have such different applications. Beyond this, of course, they will have they do tend to have several applications. So today, what we plan to do is we will start with the mechanics of rod at first, before we move on to ribbons, talking about ribbons. So let's start with rod theory. So there are, of course, several different rod theories. We have Kirchhoff rod theory, Several rod theories exist in literature. Right? Namely, of course, Quadrat rod is the most widely used one. Then a special case of Quadrat rod is what we call as the Kirchhoff rod theory. Then we have Antman rod theory, and also you'll also find something called as a Nagdi rod theory. Each of which are slightly different in the way we model them. But this is the most widely used one. And Kirchhoff rod theory is a special case of Quadrat rod. Right? So we begin with Quadrat rod theory as discussed. So in this case, what we do is, and I will be following notes by Professor sorry, Professor G.H. Or maybe I'll write the full name. It's Gert van der Heijden. He's a professor at UCL. So I'll be following his notes and presentation slides. Right. And there are many such literature, you have books on rod theories and ribbon theories. One such book is modeling nonlinear some strings and rods, we call it. So there are several such books, and but yeah, we just for this class, I'll just be following notes by Professor Gert van Heijden. And of course, there is a very good book on called Nonlinear Problems in Elasticity, which is the very classic book on this topic by Stuart Antman. That's a very nice book. Is Nonlinear Problems in Elasticity. Elasticity is a book by Stuart Antman. Right? Okay. So let's first set the background for what we plan to do right now. So let us have I'll just present a schematic for this. So we have some sort of a rod, right? Uh, a section of a rod. And of course, we are dealing with mostly circular rods. Right? Right? And say we have this and any cross section. is a tangent, and then we have normal, and then we have binormal, right? Okay. So the distance, so this is say it's s is equal to 0, and we are following the arc length coordinate as we have learned in differential geometry. So there's at some location s, and this starts from s is equal to 0, right? And at the center line here, so this is the center line. So this is the center line. The dotted, the dashed line here is the center line. Perhaps, sorry, we'll just take it to be. So here's the center line. And any position on the center line with respect to some origin, right? Let's have some origin, some fixed origin or the standard Cartesian basis. So this vector is R of S. Okay. So the idea is, so this is the schematic of a portion of RUD, right? So the RUD configuration is specified by central line R vector of S and frame of directors. Where S is the arc length, is the arc length coordinate. Now you'll ask me, why do we not use the Frene-Serre frame that we had talked about uh, in the session on curve? So the reason is it has certain issues with regard to that, since tangent is defined as the what you call as the I mean, of course, it's the derivative of the mapping of that curve, right? So if the mapping is gamma, then the derivative of gamma at any point s, that gives us the locate tangent vector. Now the issue becomes when we have a straight curve. So there's a slight digression that why don't we use Frene-Serre frame? Frene-Serre frame. So the issue is, say, the way given a unit speed curve, given a unit speed curve, gamma of s, what we learned there is that the tangent vector t of s was equal to t gamma vector by ds. And then normal vector was defined as, of course, it was 1 by kappa of s and dt vector by ds, right? And likewise, uh, and b vector, the third vector. So tangent normal, so tangent normal, and this is binormal. Binormal was equal to T of S cross N of S. Understand? So what we okay. So the problem here that we faced is that so consider as an example. Consider a say just a line, or consider a straight line, or a straight curve, or a straight rod. And this, of course, is a straight curve, right? And this say it just happens to be say parallel along E3. E3, and then we have this is E1, and then this is E2, right? So it will follow the right-hand coordinate, right-hand system. Now we start from S is equal to 0. And so as to not to fall any such problems, let's center it like this. Let S is equal to 0 start at the origin itself. Steps will be at the origin, and then we just move along this line. So any position is S, right? Until say S is equal to L. So this is our rod, straight rod till here. Now, fine. So gamma of S in this case was equal to gamma of S is S into E3, S E3, right? Fine. That is the center line. So we are straight rod whose center line this lies along and on E3 axis, right? So gamma of S is SE3, right? But to be more specific, we can just call it R of S. I mean, to be consistent with what we are trying to do here, we talked about center line, right? So R of S equal to E raised to this. So the tangent vector T of S is equal to dr vector S by ds, right? And this comes to be just E3. So till here it's fine. Okay. Now when we take a look at d vector dt vector by ds, then what we say is it's as if d3 by ds. And you recall E3 is a constant vector. So which means it's a zero vector. So which means kappa of S, the absolute value of curvature is this was norm of dt vector by ds, right? And this is just 0. Because of which, therefore, n vector of S is undefined. And so is v vector of S. Right? They're all undefined. So there is where a pitfall. So this was regarding the whole exam. This was to deal with pitfall of Frenes-Serifin. Frenes-Serifin. So here is where this director basis, or what we call as the D1, D2, D3 comes into play. So in D1, D2, D3, what we do is, so how do we, how to circumvent this problem? So what we do is we affix a different way of dealing with this situation. So what we do here is that in this configuration itself, so we prescribe a basis. So this, of course, E1, E2, E1, right? So in this case, what we do is at any point S, so at S here, we prescribe in this case a basis which is, let it be coincident with S as of now. I mean with E1, E2, 3. So this is D3 vector and it's a function of S. D1 vector as a function of S and D2 vector as a function of S. And such that, so we choose a basis which doesn't require, so to speak, which is not obtained by differentiating one against the other, right? Which is that's loosely speaking, which is not obtained, whose basis vectors are chosen by us or prescribed by us, right? By us with certain conditions, with certain properties. So the first property is that D1 vector, D2 vector, and D3 vector are unit vectors. First thing. And the second thing is R, the D1, D2, D3 are orthogonal to each other, right? So these are the two conditions that, and in this case, we have done it such a way that they coincide with E1, E2, E3. So like D3 is parallel to E3, D1 is parallel to E1, and D2 is parallel or equal to E2, right? So this is what we have done here. So here, di vector of S is equal to EI, and I is equal to 1, 2, 3. So this was this for this case. So this is a very, I mean, so in this way, we're able to circumvent the problem that we'd encountered in the Fresnel frame, right? And this D1, D2, D3, so D1 vector, D2 vector, and D3 vector are called directed basis vectors, or sometimes also called as Darboux vectors, Darboux. Right? Okay. So far, this is what we have done, right? And going back to what we had, let's make some assumptions before we move forward. So in this case, like we would just prescribe, I mean, we started with quadrant theory, but we will prescribe certain conditions because for long slender structures, that's a very valid approximation. So assumptions. And we'll deal with Kirchhoff rod because the thing is we started with quadrant, but we'll deal with a special case of quadrant. And for the just since this is an introductory course, we would not want to just bog it on with too much of conventions. So we'll just go with a simple model, which is called as a quadrant rod. I mean Kirchhoff rod theory. Kirchhoff rod. So that here we have certain assumptions. The first assumption is that it's a thin rod and with uniform cross section. It's like a thin rod with uniform cross section. That was the first thing. Right? And the second assumption in this case is that it's intrinsically straight. and untwisted. Now this has some. So it implies that we in the reference configuration we have a straight thread, which after applying loads and all, then we are able to deform it. But in essentially, it's just intrinsically straight, that it's as if even if it deformed, then we can bring it back and just it would be straight. So it's some sort of a in what we learned in the last session is that something related to as if there is some equivalent, that the Gaussian, some sort of a Gaussian curvature, right? Not exactly, but it's as if the Gaussian curvature is zero. Recall that a flat plane had Gaussian curvature zero, which you can deform into cylinder, and you can again unroll it back to a flat plane. So something like that. And it's also untwisted, right? And this then we have no extension allowed, no extension, and this is also called as inextensible. This implies that dr vector by ds, right? So the tangent by default inextensible is equivalent to unit speed curve. So it's as if this norm is equal to 1. So and this is equivalent to, or this is the same as unit speed curve. Right? So it's inextensible, and also there is no shear in the cross section, and no shear. And no shear implies that the r prime, which is just dr by ds, dot d1. So there is like there is that the plane sections before deformation, which is perpendicular to the central line, remains plane even after deformation, remains plane and perpendicular to the central line even after or deformation, right? So this one is equal to 0, and this total in totality it implies that dr vector or r prime of s is equal to d3 vector. And and one more, we have one from a mechanics point of view as well. So we have condition that it should be, there is a linear stress strain equations, right? Which means that the nonlinearities are purely geometrical. Right? Okay. So with this, what we do is, uh, let me make certain geometric observations that d1 vector and d2 vector of S, they span the cross section of the vector. Now you'd ask me, okay, but what is so just take a cross section, right? Just a segment here. Take a cross section. Just a segment of the segment of a rod, something like this. And there's the center line. So this is the center line, right? And this is the tangent, and which is d3 of S. And this will be d1 direction. And then you have d2 is perpendicular to it. So d2 of S. Right? Now what we do here is, so spanning means that any point on the cross section, any point, right? So any point on the cross section, say let it be some x vector of s vector, right? Just say it's s vector of S. So any point on the cross section, so maybe I'll just call it a point on the x vector of x of s. So this is as if the center line, the Poisson vector of the material point on the center line, which is from the origin. This will be r vector of s. So this will, of course, r vector of s plus then locally. So it's as if plus, and then we have this. We had prescribed. Let the radius be a. So let the radius. I'll just call it radius of cross section, or radius of course, cross section of rod is equal to a, which is d by 2. D is the diameter, right? So this we can have, and then we'll have one more. So a, so we will have some sort of a um, running vector. I mean, some sort of a in cross section variable, and we can call it say a tilde. So just uh, going back here. So we started with cross section where it's just so here we have been. I just need to charge it. Yeah, okay, just a minute. Okay, and so any point on the cross section will be x of s is equal to r of s plus a tilde when, and since it's the radial distance, then a tilde um, okay. So some say if say we make an angle theta with respect to d1, then we'll have a tilde and cos theta d1 of s plus d2 of sin theta d2 of s. Now the issue is, since the properties are uniform, right? So the idea is that the properties also the deformation, even after deformation, the properties are assumed to be uniform. Uniform throughout the cross section. So this means that whatever whatever the value of some property is at the center line, or I think at the cost of such tortuous wording, let's have the value of some property of a property at the center line remains the same or is uniform is maybe can be is the same as that at any point on the cross section. So because of which, and that is the major reason, or that is the actual reason why just R of S is sufficient to describe the mechanics of a rod. Right? So this is what we have been. I mean that's like a postulated, right? Okay. So now what we do is we do have the idea is that we do have the director basis D1S, D2S, and D3S basis vectors, or maybe just basis. But we have the director basis. But how do they evolve? The question is, how do they vary from or just how do they vary along the center line? Right? This comes in mind, right? This is the question that comes in mind. So in such scenario, what we would do is we require some sort of an evolution equations. So what we call such equation as frame evolution equations. Right? Then in Einstein's convention, we can just call them that note them as d1 di prime of s is equal to u cross u of s cross di s, and I varies from 1 to 3. Right? Now where u vector of s is given as kappa 1 d1 vector of s plus kappa 2 d2 vector of s plus kappa 3, and mind you that they are themselves function of s, so I should be more careful while writing down here. And kappa 3 of s, d 3 of s. And kappa 3, we often tend to call it as tau of s. Right? And here, this u vector is called as strain vector. Right? And this kappa 1 and kappa 2 are curvatures about d1, local d1 axis and then d2 axis, and tau is the twist. Right? And as we recall that this d1, d2, d3 vector are orthonormal. Right? So there is a condition, orthonormality, then, which says that di vector dot di vector is equal to 1. And then after, if we differentiate with respect to s, then we have 2 di dot di prime is equal to 0, and this implies that di vector prime dot di vector is equal to 0, right? So which means that di prime is perpendicular to di. So there is one such, and the other condition is that they are orthonormal to each other again. So di orthogonal to each other. So it's like di dot dj is equal to 0. So upon differentiating, we have di prime dot dj vector plus di dot dj vector prime is equal to 0. And then this implies that di vector prime dot dj is equal to minus di dot dj prime. Right? Now, since di prime is perpendicular to di, then we see that uh, di prime, or maybe let's start with, and this we can even, okay, we observe from the evolution equation that, say, if you have di prime dot di, this is equal to u cross di, right? And then dot di. And as you recall, u cross di will of course be perpendicular to here, and that is equal to 0. So this, it is as if we have verified this thing, right? This fact, right? So now what we would do is, well, let's look at the individual evolution equations. So d1 vector prime of s is equal to tau d2 vector of s minus kappa 2 d3 vector of s, like, and then we have d2 prime of s is equal to minus tau d1 vector of s plus kappa 1 d3 vector of s, and d3 prime is equal to kappa 2 d1 vector of s minus kappa 1 d2 vector of s. And as we recall, of course, at the cost of repeating myself, kappa 1 and kappa 2 are curvatures about d1 vector and d2 vector, and tau is the twist. And this is the twist about d3 vector. So, we have just clearly set down the geometrical description or the kinematic description of the system. Now we would like to derive the equations, the governing equations of a rod, or what we also call as the governing is, or as the equilibrium equations of a rod. So we'll deal with steady state conditions. There won't be any time coming into the picture. Right? So that is the next step of ours. So now let's talk about, which will derive the equilibrium equations. And let's do from a Newtonian form or Newtonian approach in which we balance the forces and moments, right, of a segment. Right? And of course, we can do it from an energy function as well. But let's do it just for a very without making it more, say, complex. Let's do the basic thing that we have learned through in physics, right, about force balance and moment balance for a static system. So in this case, what we have is we have again a segment of red. And let's consider this to be center line, and let the Poisson vector of this and Poisson vector of the center line at here. So this will be R vector of S, and this is R vector of S plus delta S. There's some origin O, right? So location wise, the center line here is S is equal to 0, S is equal to S, and this is S is equal to S plus delta S. Now what we have is we have forces acting on this surface. It will be the internal forces, right? So not to conflict, let's put it here. And these are the, since we have cut this portion out of the entire rod, since we have as bind them or hold them together. So on that side we have capital F vector, or maybe we can just call it n vector of S, and this side we have n vector of S plus delta S. And let there be some sort of and the distance, the segment length is delta S, and this is a very small segment. And then we have some distribute, I mean some body force, right, of, we can just call it as a vector of S, right? So, and this is one thing, and then we'll also have moments. So the moment is m vector of S, and this side the effective moment will be m vector of S plus delta S. Now let's look at the force balance. As we recall that the sum of forces acting on a body is 0, right? It implies that the sum of both external and internal forces has to add up to 0. So because of which what we can say is that n vector S plus delta S, and since it's a small segment, we can assume as if it is as if it's a uh, linear element, right? So we don't have to, they are so close that it appears to be a linear element. So which means that, so n vector uh, S plus delta S minus n vector of S plus integral of from S plus delta S, and what we are integrating here is f of vector of S bar, because S bar is a running variable here, is equal to 0 vector, right? Now this can be written as S plus delta S, and this follows from the fundamental theorem calculus that this can be written as n prime of S bar t bar S plus S of S plus delta S, f vector S bar ds bar is equal to 0. Finally, we can just add them up and bring it into into a single integrand. All that we have is n prime S plus f vector S, and then So we have this. Now, using localization theorem. So using localization theorem means it implies that as delta S tends to 0 or becomes so, it approaches some infinitesimal value, then the integrand over that region will seem as if it's a constant, right? Or in a sense, yeah, it feels that is as if it's a constant. And for the integral to be 0, it implies that the integrand has to be 0. So this is what is localization theorem. So therefore, n prime s plus. So this is the force balance equation. Now let's look at the moment balance equation. Let's look at the moment balance equation, right? So in this case, let us balance moment about the origin, right? About the origin, let's balance the moment. So first of all, we'll have m vector s plus delta s, and then minus m vector of s plus. Now we have this force acting here, right? And n vector of s, and this one will be with respect to the so we'll have r vector of s plus delta s cross, and this is the moment arm of the force, n vector s plus delta s. And then we'll have minus r vector of s cross n vector of s. And finally, we will also have the moment due to the distributed load f vector, right? So it will be s plus delta s, and then r vector of s bar cross f vector of s bar ds bar is equal to 0 vector, right? And then we'll use the fundamental theorem of calculus. So this one, we use a fundamental theorem of calculus. And likewise, here also we'll use the same fundamental. So we'll have s from s to s plus delta s. Then we'll have f prime plus. And then we would also have that r vector of s bar cross n vector of s bar whole derivative with respect to s, and then ds bar. And finally, we have s to s plus delta s. We have s rs vector rs plus f of s. And then we bring everything down into a single integral. we'll have M prime of S bar, right? And then plus R of S cross N. And we can just expand it as well. So we can have R prime of N S bar plus, or maybe let's keep it as of now. We'll deal it with later. And this is N plus R of S bar cross F of S bar. And then we have ds bar is equal to 0 vector. Again, using localization theorem. So using localization theorem, what we had is M vector prime S plus R of S cross and R of S prime plus R of S cross F of S is equal to 0. Now we'll just expand the second term, and this gives us R prime of S cross NS plus R of S cross N prime of S plus R of S cross F prime of S. And this we can simplify further as and let's look at the last two terms. So in this both the cases R of S is common, so we can have N prime of S plus Fs is equal to 0. Now when we look at the, so this is equal to 0 from force balance. Right? So because of which all we are left with is therefore M vector prime of S plus R prime of S and vector of S is equal to 0 vector. Right? So we have been able to obtain both these equations, but only in only in the form of in vectorial form. Now what we do is uh, let's write these equations in its component form. So I can just write the equilibrium equations are of a Kirchhoff rod are N prime of S plus F and also right? Okay. So we now write down, we now proceed to derive, or maybe just write down these equilibrium equations in component form. Okay. So in that sense, we will have to utilize what we call as the we'll have to use the frame evolution equations, right? So I didn't I could not mention that n vector of S is internal force, internal contact force. That's a more appropriate word. And m vector of S is again internal contact moment. And F vector of S is external loading, external body force. Right? Okay. So now what we'll do is we will say let us obtain the let us derive. So let's derive the components of n vector and m vector of S, and why not, and even F vector of S in director basis. So D1, D2, and D3 basis. So how do we do that? It's as simple, right? So Ni of S is equal to n vector of S dot Di of S, right? And Mi of S is equal to m vector of S dot Di vector of S. And likewise, F vector Fi F vector of S dot Di of S. Right? So we can, in a sense, we express it in terms of that one vector of S can be written as Ni of S Di of S. Likewise, m vector of S is equal to Mi of S Di of S, and F vector of S is equal to Fi of S Di of S. Right? Once we have this setting, now we can put it back into our equations. So Ni S Di of S prime plus Fi Di vector Fis is equal to 0 vector. And then what we do is we have Ni of S n prime of S Di of S plus Ni of S Di prime of S plus Fi S and di of s is equal to 0 vector, right? And then we use the evolution equation. So use frame evolution equation plus ni prime of s right plus ni s, and then you also have, this can be written as ui, or just u cross u of s cross di of s plus ni plus ni fi s dis to 0 vector. Now furthermore, what we can do here is that with this term we can still write it as u vector of s cross ni s di of s, right? Now take dot product. Take product, sorry, with dj of s. Then what we have is ni prime of s di of s dot dj of s plus u of s cross ni of s di of s cross dj of s, I mean dot dj of s plus fi of s di of s. I think we need more space, so I'll just shift it leftwards, including this dot dj of s is equal to 0 dot anything is 0 vector dot another vector is a 0. Scalar 0, right? So this is delta ij, and this is also delta ij because of the orthonormality condition. And this scalar product, we can write it as we can write it in a slightly different form. Um, so this is u of s cross ni dl dot dj, right? So this will give us this will give us the jth component of u cross n vector, right? So it is as if so this is as if what we are doing is u cross n vector of s, u of s, this small vector here, cross n vector of s dot bj of s. So this is as if, okay, let's look at here. So delta ij, this gives us nj prime of s, right? Plus this will give us the jth component of u vector s cross n vector of s, the jth component, right? The jth component of this plus f j of s is equal to 0. And in component form, so say in component form, we can just write this as say this can be written as just call it as say the component form is say in component form n vector is equal to n1 of s, n2 of s, and n3 of s. This is in component form, or the vector containing components is different, distinct from n vector, right? So in that case, we will have n vector prime of s plus, and this comes as u vector right? U vector of s cross n vector of s plus, and this one will be as it is, just a vector of s is equal to 0 vector, right? So here u vector of s is, and this also should be n vector of s, and we can also call it as u vector of s is nothing but these are all representations in d1 d1 d2 d3 basis. So u1 of s, which is nothing but kappa 1 of s, kappa 2 of s, and tau of s, right? So we have this in component form, and likewise in component form m vector of s is equal to m1 of s right? So therefore we have m prime of s plus right m prime of s, and all that we had is and r cross r prime of s as we recall, and this one will be again u s cross m vector plus, and r prime of n is r prime as we recall is just d3, so we'll have d3 vector of s cross and n prime nf n of s, capital N vector of s, and this is equal to 0 vector. So these are the equations in component forms. Now we have an issue here. So the unknowns are n vector, right? What n vector, m vector, and also u vector. And of course, rs vector, right? These are the unknowns. So this totals 3 plus 3 plus 3 plus 3 is equal to, we have 12 unknowns. And how many equations? The unknowns, right? And equations we have 6, no, 3 plus 3 is equal to 6. So what we see is we have some issues here, right? The issue is we are deficit by, so number of equations. So we'll just call it as E, maybe Q, say Q, this is a P. So we see that Q is less than P. So which means that incomplete, it's not a well-posed problem, right? Or maybe we do not need more information to solve for the unknowns. Right now we can clearly see that we require some further information to solve the problem. Right? So what we do is we need to find some relation between the unknowns, right? So here is where constitutive relations comes in, right? It enters the picture. So constitutive relations constitutive come to our rescue, right? So we use what we call as the linear elastic, right? Hooke's law. Linear elastic models. Linear elastic Hooke's law. So so M vector M1 of S is equal to, say, E1, Young's modulus I1, kappa 1, and M2 is equal to EI2 and M3 is equal to GJ tau. So G is here modulus and I1 is equal to I2. And these are area moment of inertia, and E is the Young's modulus. Right? And J is the polar moment of inertia. And so here oftentimes since we are using what do you call, so because of this we have three more equations relations. So it's as if we have three more equations, right? And plus depending on the requirement. So since we are using an inextensible ribbon, right? So in inextensible rod, then in that case, what happens is n prime, right? Uh, in that case, oftentimes what happens is, okay, so usually, since it's an since the rod is, or maybe just since to add to that, since the rod is inextensible, then what happens is n vector uh, is more like a reactions like term. Is a reaction term meant to enforce inextensibility. So here, depending on the situation, right? So if it's inextensible, then we will have some requirements on R prime, right? So what we see is that R prime of S, the norm was equal to 1. So we are enforcing one constraint from here as well, right? And the second is that R1 prime of S dot D1 prime, D1 of S is 0. Likewise, R2, R prime of S dot D2 of S is also 0. So we have one constraint and one constraint. So effectively, we have three constraints, right? So this will also add up as plus three equations, plus three constraints. And this three will be from this, I will just call it plus three. Yeah, what do you call constitutive relations? Constitutive relations. So effectively, we have 12 is to 12. So n vector comes out as a during the solution. So that's what we have to talk in this red theory, and this is like a very, it's more like a crash course that we are trying to do here. What happens is we'll also prescribe some boundary conditions. Of course, to close the problem, we need to so what we do is we also prescribe at S is equal to 0. What are the conditions? So S equal to 0, you have to prescribe everything like D1 at S is equal to 0, D2 vector at S is equal to 0, and D3 is equal to X at S is equal to 0. So this is prescribed. And usually we take it to align along the canonical basis, and then we start from the solution from here. And then we use the evolution equation to move forward. And kappa and everything, these equations are a part of these equations, right? So these equations, this as well as this becomes an equation in terms of kappa and all, right? With terms of kappa 1, kappa 2, kappa 3. Right, so it and this one will be in terms of n1, n2, n3, and that's how we solve the equations, right? So in a sense, we have lots going on. So we have a set of multiple, as we recall, we have set of 12 equations furthermore, and also the evolution equation in D1, D2, D3. So we are solving 15 equations at one go, and that's how we have a quite a big set of equations to solve for. And at S is equal to 0, also we'll have S is equal to L. We will also have some based on depending on loading conditions, depending on loading scenarios. Right? That's how we solve this problem. So this was a very of Rudd equations or Rudd theory. Now we'll briefly mention about the the Riemann theory. And we'll just close the lecture for today. Okay. So let's briefly mention about Rudd theory, about Riemann theory. And this requires a separate set of lectures to understand this, but just because of the paucity of time for this course, as well as that so that we do not go out of scope for the course, right? I will just briefly will mention about Riemann theory. And there are also several theories in Ribbons as well. So one of the prominent ones are the Wunderlich ribbon theory, ribbon model, and a special case is Sadowski. And so these are uh, so we have Sadowski's ribbon model. For further information, I would refer you to papers by Basil Orderly, and then Heisden, the one we were referring to, Heisden. So these are some of the prominent people who have done work in this area. Okay. So okay, let me just and these are this have to do both these models have to do with they have to do with they differ in the energy formulation. In their energy formulation. They differ only in energy formulation. The geometric description remains so the geometric description remains the same in all cases, right? So let me start with brief geometric interpretation. Okay, the pen, sorry if I could not charge it. So let me. Right. I hope it's charged. So essentially, in all these theories, what we do is we first construct some models, the energy function models, and then derive the governing equations. So that is how typically it's done. Right? And they will usually be in a similar form as the red equations, except that we have the what do you call the constitutive relations would be a bit complex. Of course, it has to be, and then also since we introduce the transverse dimensions, so that also creates some complexity in the equations. Right. So that's where they differ. Okay. So coming back to the geometric description or the kinematic description. So say we have a ribbon like this, a segment of the ribbon. And of course, we have a center line. Consider some point here. I should have used some other color for the center line. Simply this. So say we have the center line, and then they are ruled surfaces, right? So they are ruled surfaces. Okay. And then say we have consider this, and this is our center line as usual. It is denoted as r vector of s, right? And we consider one such ruling, and the local tangent is t vector of s. Use a different color. So t vector of s, and the normal is given to the surface as n vector of s, and then the binormal, right? So t cross. So ideally, let's not use all this, like we should use the director basis as is typically done. So this is d3 of s, and we will have this to be the d1 of s, right? And then d1 cross d2, right? So we'll have, say, d1 cross. So there's some formulation here. So let this be let this sideways be this be the d1 of s, and vertical to this be d2 of s. Then it follows the right-handed system rule, right? d1 cross. Let this be some equation, some angle between these two, and just we call this some beta, right? Okay. And now we have, I think, completely geometrically described, geometrically, figuratively, we have explained the terminology. Now let's look at the parametrization of the ribbon surface. Parametrization of the ribbon surface. And we do so by taking x vector of s at any point is equal to, of course, it's a 2D like object. So we have r vector of s is the central line plus t runs from one end to the other end. It is along the ruling. As we recall that we had gamma u plus v into delta of u, right? And this was sigma uv. So comparing it with, so x vector is like sigma, uv are like s and t. And then delta of u, v is like t, and delta u is what we are going to construct now. So delta of u happens to be d1 of s plus eta of s, and then d3 of s, right? And so on comparing with surface paths, we have this surface paths. What we have is u is equal to s, or at first sigma bar is equal to x vector, and u is equal to s, t is equal to v is equal to t, and then gamma vector of u is equal to r of s, right? And then we have delta of vector of u, which are the rulings, right? Is equal to d1 of s plus eta of s, d3 of s. So these are the rulings. Right? And here S is an element from 0 to it belongs to the set 0, 1, 0L. And to my knowledge, it was a small L, right? Let's go back and see. Yeah, it's small L. But maybe I'll just revise it so that we don't have problems here. Otherwise, it often becomes an issue. So let me revise so as to remove any inconsistency. We'll have this as W, and let's call it as H. So H is thickness, and this let it be W. Right? So, okay. So this we have, and T is an element from minus W by 2 to W by 2. Right? So, and of course, eta of S is equal to cot of beta of S. And if the rulings were perpendicular to the tangent, then beta would have been simply pi by 2. Right? And then it implies that the director base, the rulings would have been just d1 vector. So it would be d1 vector. Right? Okay. Now, let us look at the first fundamental form. So we'll have x vector of S is equal to R vector, maybe I'll just call, yeah, and RS plus right, and then T d1 of S, d1 prime, I'll just call it R1 R prime of S plus eta prime of S, and then d3 prime of S, d3s, and then plus we'll have additionally eta of S, d3 prime of S, right? And we'd have a separate and likewise x of t would be some sort of an expansion like this. We can fill in the gaps by knowing the d1 d2 prime from the what we had learned back, and then x of t is just d1 of s plus eta of s, d3 of s, right? And then likewise, we would have the first fundamental form as xs dot xs is equal to something, f is equal to xt dot xs dot xt. I'll complete it in the notes and then send it to you. So do not worry. G is equal to, right? G is equal to xt dot xt, which can be done right away. So it's like d1 plus eta d3 dot d1 plus eta d3. And they are orthogonal to each other, so they have 1 plus beyond this is 0, and then the cross terms are always 0, and then we have eta squared, right? And now we'll also, for the second fundamental form, we look at the n vector, which is the in this case the d2 vector, that is the to the surface, right? So all that we need to do is we can also have L is equal to minus. So here n vector of S is nothing but just d2 vector of S, right? So therefore, we can have the this one is equal to minus. Of course, we had xss dot n vector of S, which is d2 vector of S, which right d2 vector is normal, and then this could also be written as minus x vector S dot d2 vector of S prime of S. Right? Then we have some expression. I'll fill it later and then show you. And then m is equal to xst dot d2 of S, and this is to saying minus x vector of S, and then we have d2. Now we can also write it down as t dot d2 prime, d2 prime of S. And will this going to be a okay? D2 prime is, of course, it belongs to the same set. So this is the, and then eventually we have n is equal to xtt dot d2 fs. Vector of S with respect to t, which is of course 0. So we'll have just minus 0, or it's just 0. All right. And mind you that the Gaussian curvature k is equal to ln minus m squared divided by ef eg minus f squared. And recall that n is 0, so it means it's just minus m squared. divided by Ag minus f squared. And as we recall, is less than 0, as we had learned, less than or equal to 0. And the condition for developability, condition for develop of the surface is k is equal to 0. And we have the condition that eta is equal to tau by kappa. Right? So furthermore, what we have is um, that we can look at the mean curvature and also the area element, right? So finally, we have the bending energy. And it so happens that bending energy is just a function of one principal curvature. Since it's the Gaussian curvature is 0, it implies that one of the principal curvature is 0. So let's only have kappa 1, which is the non-zero one, and then dA, right? And then this can be integrated in terms of, so this will vary from 0 to L, and this will be from minus W by 2. And W by 2. This comes out to be we'll have dW, and D is the bend, some what we call as the flexural rigidity of the cross section in this case, right? And then we have 0 to L, we have G, kappa, eta and eta prime. And this kappa is some sort of it's a different functional, which is more like a principal normal, a principal curvature. And then so it depends on Sadowski, and different models will have different expressions for. So the expression of G varies among different models. Right? So this is eventually the elastic energy, and then we use all those concepts from variational calculus. And then derive the governing equations. And I think with that, we'll close this lecture here. And yeah, it has been quite an experience for me for teaching this course for the first time. Yeah, I have learned a lot during this journey, and thank you for watching the videos. It's so okay. And yeah, please get back to me if there are any doubts. You have my email address, which is Krishna AAGR at iisc.ac.in. So this is my email address. You can get to me, or Of course, my name is G.R. Krishnachandra Avatar. Okay. Thanks, everyone.